Thanks. Thank you for having me here. So there's a session that is about this which I'm going to start, and it's about this phenomenon of light-induced superconductivity. This is comes from a number of results, primarily from our laboratories, where one uses light to take a material that typically wants to be superconducting up to a certain temperature, and then has some features that one can identify in the optical spectrum that one can observe in particular stimulated states above, in a non-equilibrium situation above the thermodynamic transition temperature. And these are experiments actually that have raised a lot of discussion, because sometimes these features are observed all the way to room temperature. I think, and I'm going to say two things about this. Firstly, that the physics that is emerging is completely different from the hypothesis that we made at the beginning when we started doing these experiments, and I'll try to guide you through those. And that whether this is exactly superconductivity or not, it's not really clear, except that what is becoming clear is that this is really a very remarkable set of phenomena that need to be understood, and that do bear some close relationship with superconductivity. And what they teach us about the ground state or about the driven state is what we're going to work on. And the last thing that I'm going to say, I'm going to start by apologizing, because I think the way I'm going to walk through this talk is going to cover you with details. I thought it was a good time to review all the evidence. So for those of you that are not so expert in optical spectroscopy, you may get lost a little bit here and there, but I'm going to try to do my best to sort of combine information with fluff. Okay, right. Okay. So first statement. There's about hundreds of years of materials control. I always think about 100 years, but maybe we should think about thousands of years on how people control materials. You can change. This is a phase diagram in which some phenomenon lives under these phase domes. So you can change the stoichiometry of a system, or you can apply typical stimulation such as pressure or things that you do only at equilibrium. But by and large, this is a type of materials discovery that explores phases at equilibrium. And so, of course, when solids are being driven away from equilibrium, then there may be qualitatively different phenomena, simply because on average, when a system is being driven to high amplitudes with a high frequency, there is an effective let's say there's an effective energy of the system that then may give rise to completely different states. So that's statement number one. And this is sort of one of my favorite things. This is the well-known Kapitsa pendulum, in which by shaking a pivot of a pendulum fast enough, one can find new stable states of a simple pendulum, in which, in this case, the theta equal pi point becomes a stable or a point. And this is by virtue of the fact that you're shaking your pendulum at a frequency that is high compared to the eigenfrequency of oscillation of the unperturbed pendulum. So there's a number of similar phenomena, such as this business of the spinning saddle, which is the way we make ion traps. You take a saddle, and which is unstable, and if you spin it fast enough, you'll create minimum potential. So this is some sort of simple teaser of why do we want to spin things fast, and can we do this in materials, and can we find new states of matter in the driven state. Second statement, or third statement, is that if you want to use an electromagnetic field, for example, to modulate at high frequency, to modulate a solid, and you want to have a particularly effective way to couple this modulation field to the state or to the collective properties of the system, there's at least one candidate that can make it possible for you to do this, which is to go through the structure. This is there's this exponential dependence of the electronic properties on structure, and here I'm plotting my four very sort of classical examples of how, by changing a single bond angle in four solids that all have one unpaired d electron close to the Fermi level, that look almost identical, except for one particular angle that bridges two cations and bridged by an oxygen, how one, by changing this angle by only a few degrees, one can go from a metallic state, weakly correlated or almost non-correlated metallic state, to a highly interesting correlated ferromagnetic insulator. Okay, so in principle, there is a very strong connection between individual degrees of freedom of a solid and the collective properties. And if I could, what I would like to do is to go there with my little finger and move one atom from here to there, or shake it up and down, and then see what happens. Okay? So of course people do this with pressure, they squash things or they change. But of course when you apply pressure, many more things than a single bond are effective. So we would like to do something like that in a slightly more surgical manner. Right, so the whole talk is going to be about the use, about modulating the structure of solids by using terahertz and mid-infrared radiation that couples onto infrared active lattice vibrations and shakes them. And because these, depending on the polarizability, these fields that are resonant with a mode of the solid of many megavolt per centimeter are actually not that hard to make. And if you have a field that has many, let's say 10 megavolt per centimeters and is resonant with an odd mode, you could drive the atoms to let's say many percent, 10% of the unit cell. And so now we're thinking of almost like a cold gas experiments in which one sort of shakes the lattice and looks at the new average properties. Okay, so that's what I would like to do, is to take my yttrium, yttrium titanate, and make it strontium vanadate, but not only periodically, but hold it there in some sort of average new state. And this is I'm not sure what this is. This is supposed to be some free energy, and with a hidden pocket that I'm reaching, that I could not reach otherwise, with a large kinetic barrier, and I would like to, in the laser field, stabilize this state. Okay, so the important thing is that if I want now to come with my light field coupled to one normal mode of the solid and displace the structure, this is easier said than done. And the reason for this is that if I consider the response of a lattice to, say, at least in linear, to most orders, the response of a lattice to light is one in which the modes or the charges are not displaced. So if I think about the response of a spring to an electromagnetic mode, this will be that of a damped harmonic oscillator with zero average. And this is because the field comes in, has zero vector potential, comes out, and in principle leaves the lattice undisplaced. So if I want to take my yttrium titanate and make it strontium vanadate, or vice versa, I cannot do it simply, as we were thinking at the beginning, by exciting that particular mode. So one needs to do some more thinking. So of course, we are familiar with situations in which one can drive a lattice, for example, thermally, and one can find itself in a displaced position, for example, by thermal expansion. So there's anharmonic phenomena that average out all the fluctuations and give me a finite displacement of finite average. So we think about, in the same way that we think about nonlinear optics, we can think about nonlinear phononics, and we can look at how a particular linear mode, when driven to large amplitudes, couples to many other modes according to various rules, etc. And this is kind of a big part of this, in which instead of driving simply a mode linearly and shaking it close to its average position, we exploit the coupling of this infrared active mode that I'm driving to one or a subset of other modes, which we're hoping, this is time now, and this is the red mode, is the one that I'm driving with my light field, and I'm going to try to displace in other modes that are coupled anharmonically to it. Okay, so this is, in the context of nonlinear optics, this is the equivalent of optical rectification, which is, those of you that know about nonlinear optics know that in a particular second order nonlinear term of the nonlinear polarization gives me a rectification of the field. Okay, so let's see. Let's think about the energy of a mode, and the energy of a mode, which is my IR mode, has this linear response where the energy is proportional to the square of the mode coordinate. And then let's add the first correction term. This is the first correction term if the system is centrosymmetric. And let's say that I have something that depends on the square of the mode that I'm driving and linearly on another mode. And what this means is that if I think about this term in a frozen phonon, if I move my IR mode and then I stop there, what this means is that the minimum of potential of the other mode is going to shift, okay? For the same reason that, this is the same physics of thermal expansion. All right, so let's think about, so if I have decided that this is the lowest order nonlinear contribution to the physics of these bonds, and I'm going to think about the equations of motion of these two coupled modes. Okay, so this is the mode that I'm pumping, which, as I said, I have a laser that is a sine wave, and then I have this damped harmonic oscillator, and this is the Q coordinate of the IR mode that shakes, and this is the pulse that is gone after a while. Depending on the details, the mode will ring for something that is if the line width is 5%, this will be 20 swings, and then the mode will dampen out. Okay. And now, if I think about this term, and I think about the equations of motion, what will happen is that a second mode, which is coupled in this Q square Q term, will be driven not by the laser field, but by the square of the Q1 coordinate. Okay. So what I will have is a force on the mode Q2, which is the square of a sine, which has got a finite average, and then it will. So what I will have is that the Q2 mode will have two components of the force. We'll have a force at 2 omega, and then we'll have a finite displacive force. This is because sine square is 1 minus cosine 2 omega. Okay? And so now the second mode will respond like so. Will be displaced and will ring for a while. Okay? So that's kind of the basic of the way we're thinking about controlling these materials, and we've restricted ourselves to this term of nonlinear phononics. Obviously, there's many other opportunities that I won't belabor here. Okay, right. So this is what I said. There's two pendula. One shakes, and the other one, on average, experiences an average force, and maybe shakes a little bit at 2 omega if some resonant condition is fulfilled, but primarily is displaced. Okay, and we've used this, for example, to drive transitions in manganites, which I'm not going to tell you about, in which one has a distorted structure and crooked bonds, and one makes them more straight by selective phonon excitation, and you can drive an insulator meta transition by these means. Okay, so that's a little bit of background about what this lattice shaking is. Good. So this is now to the top. I felt I really needed to explain this thing because otherwise I was just going to say too many things. Right, controlling superconductivity. We want to take a superconductor, and instead of shining light to destroy the superconductor, which seems to be a very popular activity in my field, what I would like to do is to shine light to improve the superconductor. And there's at least 2 reasons why this might be possible. Reason number 1 is that in some cases, for example, in the cuprates, which is going to be the first part, what I know is that at some specific dopings, for example, 1/8 doping in the cuprates, one has specific density waves that are coupled to frozen phonon distortions that quench superconductivity. Okay? So in the case of, say, 1/8 doped single layer cuprates, one has a system in which the mean field, somehow the system would like to be a 40 Kelvin superconductor, except that if there is a frozen lattice distortion that makes it a 1 Kelvin superconductor. And so there's an idea that if I can destroy this buckling, I can reveal the hidden state. And I can, for some time, as long as the hidden state wishes to stay there, or for however long, I can keep my laser going without frying the material. The second thing, which is even more esoteric in a sense, and who knows, is one in which one thinks about superconductivity as being mediated by phonons, and the question is whether one can use some appropriate control of the phonon field to stimulate pairing or stimulate synchronization between pairs that are already there, or something of that nature. Okay, so that is as you will see, the results of the talk will bring me further and further away from this idea of the competing order melting and the creation of the transient state to more exciting and yet puzzling results. Okay, so these are the marching orders. I'm going to tell you first about this and then about this. Okay, first thing. So this is actually, when we started doing these experiments, we thought, okay, let's just take this cuprate this is a phase diagram of lanthanum barium cuprate. Take it as a placeholder for single layer cuprates. And this is Tc as a function of doping. Normally, remember, as you dope the system, you have a dome that peaks at 16%, where Tc is maximum in this family of compounds is about 40 Kelvin, and then it kind of disappears. And this is a phase diagram for lanthanum barium cuprate in which a competing order, which is this stripe order in which you have charges, rivers of charges, and oppositely phased antiferromagnetic domain and a lattice distortion, come in and reduce Tc, in this case, to say 6 Kelvin or something. Yeah? At 12.5 doping, which is where the stripes, you can fit 8 stripes in the periodicity. Okay? And so when we started, we said what we're going to do is we're going to pump this guy and we're going to make a superconductor all the way to its T mean field temperature, which is, say, 30 or 40 Kelvin. We'll write a science paper and be done with it. That was the plan. And maybe we can, squeeze out a couple of Kelvin and write another PRB. Okay? So all right. So going back to this business, one of the key features of these striped cuprates. Let's now consider a cuprate without stripes, which is one like lanthanum strontium cuprate, in which this effect doesn't happen and Tc looks like a nice dome, and a system like europium doped lanthanum strontium cuprate, which is the most extreme of these stripe states in which superconductivity is quenched. And let's think about one feature that is easily seen other than resistivity, the DC resistivity or the Meissner effect, that can tell me about the superconducting state. Remember, this is a state with a complex order parameter, so it's not that simple to look at gaps in optics. And anyway, there always a little bit of criminal fitting that comes with fitting gaps in optics. Okay? One thing that until our experiments everybody would have sworn is one-to-one related to superconductivity is the presence of this particular edge in the reflectivity of a cuprate below Tc when the material is cooled below the transition temperature. So this is a plasma edge that one observes with the electric field polarized perpendicular to the planes that has got to do with the fact that the order parameters in the planes are coupled in a way that the phases of these orders are correlated. Another way to say this is that the C-axis electrodynamics of a layered cuprate is basically LC electrodynamics because you have inductive tunneling and capacitive planes. So this system has got a resonance and it rings like a bell if you perturb it, and hence you see this plasma resonance that tells you that is very long-lived, as you can see from the fact that this edge has a relatively small width compared to the frequency, and the position of this edge tells you about the superconducting order. And so if you now go into the material in which the stripes destroy superconductivity and you go above Tc, which for LESCO is effectively 0, and you probe the reflectors in the same way that you did in the optimally doped cuprate, you see no plasma edge. And the reason is that a cuprate above Tc has RC electrodynamics, which don't have a resonance. Basically, you have resistive transport between capacitive coupled planes, and so you have no resonance. Okay, so we would like to take this and make this with our light field. So the protocol or the hypothesis is we should come with light. You have these stripes, shake the lattice in the correct way with all my couplings, melt the stripes, and then make sure that the tunneling appears. So I'm going to tell you the story the other way around, but let's say that what we want to do is first to prove that you can melt stripes with light. And so you need a method that allows you to look at stripes, which remember are a super lattice in charge density and spin density over your registered lattice. And so to do this, what you can do is a resonant soft X-ray. Remember, there is let's say a tenth of a charge is being modulated on top of Z-square charges that give rise to X-ray scattering of all the systems. So the only way you can look at this super lattice is by going resonant to some edge and still accumulate for a long time. So if you go resonant with the oxygen K edge, you can look at the supermodulation of the p electrons, and with 10 to the minus 9 efficiency, you can see a particular peak at the wave vector of the stripes. And this was demonstrated with third generation synchrotrons only about 10 years ago. Okay? And so we would like to do this in the time domain, pump the lattice, and then come with a second pulse that is intense enough to measure the stripe peak and see it go away first. So the reason why this is becoming possible, a little bit of advertisement of the wonders of modern laser technology, is the fact that nowadays we have X-ray lasers which are being generated at great cost of taxpayers' money by taking accelerators and accelerating electrons to, say, 10 GeV, in this case 15 GeVs, then passing these electrons in an undulator and relying on the nonlinear physics of the relativistic electron beam and the emitted X-rays to generate femtosecond pulses of X-ray radiation with a lot of photons in them. And so in principle, one can go there and synchronize one's laser with this accelerator, pump the phonons, and use the X-rays that come down this pipe to measure the stripes. Okay, so we do this experiment, and what we want to do is, again, we go to the LCLS, which is the only functioning laser up to yesterday, I think in Hamburg. There's now finally a functioning laser, at least there's light coming down the pipe. One can pump the phonon, go to the oxygen edge, and look at this super lattice peak. And sure enough, after lots of work, what you can see is that a peak that was a negative time delays before pumping was associated with the presence of stripes. In YBCO goes away, let's say at least 70% of the stripes go away. Okay, so now I can kind of think that with these ideas in mind, if I go now into my stripe cuprate and I measure with optics the low frequency reflectance, I should see the appearance of a plasma edge where the plasma edge was supposed to be, if the system did not have stripes. And so this is, again, it took a while, but what you can do is this is the transient change in reflectivity, number of details that I'm happy to take if you, answer if you're interested. But in principle, one can show that an edge in the system, in the reflectivity of the pumped system, in this material in which TC is effectively 0, can be induced if one melts the stripes with light. Okay? And more work has shown that you can see this edge all the way to the stripe order temperature in LESCO. And maybe if you squint, you can even see it all the way to the charge order temperature. But anyways, this is somewhat broadly consistent with the idea in which one can only induce superconductivity or transient plasma edges up to the temperature where the stripes were there to start with. Okay? So this is somehow broadly consistent with our hypothesis. Right, so this is the hypothesis we're working on. So let's take another system. These are the bilayer cuprates. Bilayer cuprates are important because they were the first cuprates that superconduct above 70 Kelvin, above the, anyways, at high enough temperatures. And YBCO is one example, is one in which one has many, this is an incarnation of one of the many phase diagrams of YBCO, but you can see that there is a superconducting dome, a depression of the superconducting dome, close to 1/8 doping, mysterious charge and spin density wave that takes place here, some nematicity here, strange, this changes by every year, and then this mysterious T star line that defines a place, a region of phase diagrams in which some people say there's preformed pairs that are fluctuating, other people say there is a different set of order that sets in, but anyway, broadly defined. This is a gapped state that in many ways looks like the superconducting state, but it's just not superconducting, okay? And so in principle, one could go here in this charge density wave, which is a cousin of the stripe state that I told you about, try to melt the stripes and do the same thing that we did. So what's interesting about YBCO, for example, is that there is actually a number of experiments that indicate that there are indications of pre-existing coherence between these planes. This stuff here is supposed to indicate that there's Cooper pairs or some sort of superfluid that tunnels between the closed space layers. And there is some evidence that has discussed the presence of these preformed tunneling features or pre-existing tunneling fluctuations all the way to 180 Kelvin for some dopings for a material that doping is, say, a 40 Kelvin superconductor. And also that there are peaks that have got to, in scattering, that have got to do with the presence of these superlattices. So what we do is we come and we do the same experiment that we did before, except that we pump a different type of phonon for a number of reasons that I will not tell you about, which is, however, this is this apical oxygen mode that modulates the position of these atoms to and from the superconducting planes. These are the two superconducting planes of the unit cell. And in this way, try going to either in the CDW or below TC and try to revive or strengthen the superconducting state. Let's see. First, this is something I added about 10 minutes ago, but I thought this was important. First, what happens below TC? You take this material that is already a superconductor below TC, and you shake this particular mode. Now, in this material, because you have two sets of layers, you actually have two edges. You have one plasma edge between the bilayers and one plasma edge within the bilayers. And you can see this in reflectivity. There's this edge here, which is similar, which is this one. And then there's this thing, which is an edge, and the zero crossing of epsilon 1 is shown, where is it? Yeah, here, in the inverse of epsilon 1, that shows the existence of two modes and mixed modes, okay? And the position of these edges tell you how strong the tunneling is between this and between that. And so at equilibrium, if you measure the reflection below TC, you can find three edges for three dopings. If you increase the number of holes into the layers, you can find that edges are found at higher and higher frequencies, which is because the superfluid becomes denser and denser, and hence the inductive coupling becomes stronger. So if you come in this situation in which you already have an edge, and you now pump the apical oxygen mode, what you find is a change in reflection, which actually can be reconstructed to show you that there's a consistent blue shift of the plasma edges, as if the coupling between the bilayer was becoming stronger. And if this were to happen at equilibrium, you would say, well, this has got to be a higher temperature superconductor because the superfluid density is getting larger. And you can see this even more clearly if you plot the imaginary part of the optical conductivity, which tells you about the superfluid density in one particular direction, which in a good superconductor is supposed to scale like with a 1 over omega dependence, so diverging as the frequency gets smaller. And what you can see is that if you start in the gray state, which is already a well-recognized superconductor, because this is apparently a very clear 1 over omega response, and you pump the system, what you can find is a much stronger 1 over omega response in the driven state. Again, indicative of the fact that your superfluid density is getting stronger. So long story short, we've done a lot of work, and what we found out is that there seems to be a transfer of spectral weight between these junctions and this junction, and something that appears not to be creating any new Cooper pairs. That's kind of the take-home message of this paper, which is that you don't need to create new spectral weight to explain the appearance of this blue shift of the plasma edge, but you can simply transfer spectral weight from this bilayer. As you can see, this red peak is shifting to the red, and to justify the fact that this edge shifts to the blue. Okay, so this is somehow, this is at least one piece of information that we were able to find out. And more interestingly, now let's think about what happens above TC. I told you that the interbilayer tunneling becomes stronger, suggesting that the system might be a higher temperature superconductor. So we look at this same plasma edge. Where was this? Right. We go in this system, which below TC has got this edge, and above TC does not have any edge. And so we go above TC, and we pump the apical oxygen. And what you find, again, this is the edge that I showed you at equilibrium. This is the inverse of epsilon 1, which tells you that there's a zero crossing in epsilon 1. And what you find is a light-induced edge pretty much at the same frequency where the equilibrium edge is, at temperatures that are 2 times larger than equilibrium TC. So this is a 50 Kelvin superconductor, and you can find a very nicely well-formed edge and the zero crossing in epsilon 1 at 100 Kelvin. So, however, this is still at 1/8 doping, and this is broadly consistent with what I told you before, what you have is that this is the equilibrium peak that tells you about the presence of charge order. The equilibrium peak goes away approximately at 150 Kelvin, and my light-induced state basically goes away with the presence of the peak. So this data, every time I've measured a 1/8 doped compound, I've always found the same response. The light-induced state appears to emerge from a melted competing order state. Okay, so 1/8 again is something that confirms okay, these are again LCLS data that show that, we do the same experiments, and we show that this particular peak melts and in conjunction with the appearance of this plasma edge. Okay, so the hypothesis at 1/8 doping still stands. Now let's look at lower doping, and the reason why we want to look at lower dopings is that charge order peaks at 1/8 and then goes down. So this effect should get weaker and weaker when the doping is being reduced. Okay. And surprise, so this was the strength of the light-induced state, which is recasted here in some effective medium theory. Again, happy to take questions about this. I won't discuss it. And when you see at 1/8 doping in the 6.6 compounds, you have that the light-induced state disappears at about 150 Kelvin, but it becomes stronger and stronger as the doping has been made smaller. So this is inconsistent with the idea of melting stripes, because the stripes are getting weaker and T star is going up, and all of a sudden I am creating a stronger and stronger putative light-induced superconductive state as I am reducing the doping. Right, there you go. This is my point. So this is the light-induced plasma edge, which in this case, and this is the result of a mean field fit, because we can only measure up to 300 Kelvin, and then we haven't heated too much. But let's say that this is our best guess of where this light-induced TC-like fit disappears. And we can see it follows something that is similar to this mysterious T-star line. As if, so if you ask me, I would tell you that, and after having discussed this for many, many years with people, I would say that already in this T-star, under this T-star dome, there is something that is very maybe preformed pairs or something like that is very similar to the superconducting state, and by driving the system, one is effectively either synchronizing pre-existing pairs or amplifying these pre-existing pairs or something like that. Okay, but this is really the observation, which of course made the whole thing very difficult, A, to defend, and B, to get published. Also because basically we're claiming that there's a light-induced transient superconducting state all the way to room temperature, and parenthetically that cuprates appear to be a failed room temperature superconductor in some way. Okay, so this would be the logical conclusion of our result. In failed superconducting state, in the sense that there is some pocket somewhere in free energy space that can either be activated or... Oh yeah, sure. Yeah.
Just to understand, so it means you heated up the sample to say 300 Kelvin? And
this is the base temperature.
Right.
This is the base temperature. You're in this pseudo-gap phase, which is below this line. Yeah. This mysterious, which is a gapped state with a D wave and everything, but not superconducting. And then you do shaky. Yeah, and then you see this edge, which everybody would have sworn was related to the equilibrium superconducting state, and it's at the same place where you find it in the same material when you cool below TC. So
the data point is down all the way up to there. You see the shift.
Well, this is what we see. I mean, we see the data up to here, and then we make a fit, and this is the point I'm plotting where this fit goes to 0. Okay, but you see broadly in this case actually in the 6.45 the light-induced effect at 300 Kelvin is basically the same as the light-induced effect at 100 Kelvin. So you can see, I mean, this is really a strong effect. Eugene, you were asking something.
So how long does this transient superconductivity last? Is it also picosecond?
Right, depends. In the 1/8 compound, for example, in the LESCO, where you have this real sort of stripe melting and such, it can last many, say more than a nanosecond at low temperatures. In this case, instead, it lasts anywhere between 3 and 7 picoseconds, depending how you fit the data. Okay? Let's say more 3 than 7, probably.
We see just this wave coming back from superconductivity now?
No. That seems to take a longer time, although remember at free electron lasers, you take one curve and that's about it. So the answer is I don't know, because I don't have a systematic study of the recovery time. But broadly speaking, what you find is that your charge density wave goes down and stays down, presumably because the kinetics for the regrowth of these superconducting domains has got to do with more complex phase 2. Yeah. Yes.
How does the result depend on the fluence, like this last slide was showing the space dynamic plots?
Yeah. Right. Okay. I'm going to say more in the buckyballs about this. The way it works generally is you have. Can I write here? No, maybe not. That's not a good idea. Basically, what you have here, you have a threshold below which you don't see anything, and then you have a linearly increasing signal with fluence, and then we don't have enough light to see it saturate in this material.
But there's no limit where ultimately it's heating and you are like systematic way in which you can control it.
I mean, the heating, remember, there's an impulsive excitation, and then there's a relaxation, which we don't understand. This relaxation may involve simply heating or something of that nature, but yeah, I mean, heating in half a picosecond, usually, you're in a highly non-equilibrium state, so depending exactly what you need by heating, yeah. Yeah, Martin, yeah.
One last question. So what I don't understand, I thought this plasma edge only occurs in the first place when you have superconductivity.
Yeah.
So and only then you can see a shift of it, right? If it's already there, you can see a shift.
Yeah.
So how come at like, say 300 Kelvin,
So
you see a
below
shift of something that doesn't exist? No.
Below TC, you have a plasma edge at 2, and you see it at 3. I don't know what 2 and 3 are, but let's say. Above TC, you have a plasma edge at 0, because the superfluid density is 0, and then you get a plasma edge at 3, which emerges like Venus out of the waters. You didn't have it before, okay? So that's the observation.
So the percentage increases infinitely, though.
Well, the percentage increase is such one in which you recreate the plasma edge that you observe, give it or take it 50% of the position in the same material at 0 temperature. It's not that you find an edge in a strange place that you wouldn't. And it scales with the other thing that is remarkable is that the light-induced edge, sorry, I always envy people that can zoom. Right, I know this is asking for trouble, right. When you have the light-induced edge, this is the equilibrium edge, the light-induced edge at these 3 dopings shifts to the blue also with the base doping. So there is some degree of correlation with the ground state properties, yeah? Okay. Corina, how much time do I have?
Go on.
Great. Okay, I want to tell you another thing at least. All right. So you're. Okay, I'm gonna say a few things more. Dynamical modulation. What is going on? I've told you nothing basically of what's going on with the lattice. So now going back to our game with the nonlinear phonon excitation, if you believe this whole business of nonlinear phonon excitation, you will say that this is a particular mode that you're driving, and this will couple in Q square Q because of various selection rules to 9 modes, totally symmetric modes of asymmetry. And this in Q square Q is the only thing because the square of B is A in this particular crystal structure. So in principle, if you could measure, well, you could either calculate a lot and measure 1 Bragg peak, or you could measure 97 peaks, which are 3n of the number of unit cells, or go somewhere in between. Let's say you want to measure 9 peaks and try to reconstruct the transient crystal structure of this putative room temperature superconducting state. So I'm going to show you 4 peaks that we measured because other peaks did not show a large result because of various reasons of how much each mode couples to each. But you can see that you can fit the response of YBCO 6.5 in hard X-ray scattering at the LCLS with only one free parameter, which is the N plus relaxation, which is actually the amplitude of the first mode that you're driving. And then you can apply nonlinear phonon theory using first principle DFT calculations, and you can have a vastly overdetermined procedure to give you a transient crystal structure of where all the atoms are in the perturbed unit cell by doing these hard X-ray diffraction experiments. I've explained it really badly, but I can tell you more about this. The most important thing is that if you do all this and you measure the peaks, you find a transient crystal structure in YBCO 6.5, in which a number of things happen. You find that the buckling along one direction in the plane becomes stronger, the buckling along the other direction becomes weaker, but most importantly, this apical oxygen shifts on average. You're moving it up and down, but it also shifts on average by about 3% closer to the planes, okay? And if you look at what people have done with pressure, when people apply, people have, of course, taken YBCO 6.5, applied pressure and measure TC and the lattice structure. And what they found is that in this particular material, you could have changes in TC as high as 15 Kelvin for changes of the apical oxygen about 0.5%. And then if you try to move the apical oxygen more than 0.5%, the crystal would crack. And so in this case, what we're doing is we're moving the apical oxygen on average 6 times more than this. So I'm not really sure I believe this, but one could say, why not? Maybe all you need to do is to create a crystal structure in which the apical oxygen is 3% closer to the lattice, in which case you will have made a better superconductor. So, but this is at least is a fair comparison between a transient crystal structure determined by X-ray scattering at a free electron laser and an equilibrium crystal structure under pressure. Right, okay. Is this phenomenon general? Which brings me to what we're working on these days. Again, I promised to you that we were going to think about experiments in which the superconductivity is slightly better understood and in which electron-phonon interaction is known to be mediating superconductivity. Okay? So we're going to look at a completely different material, which is this potassium-3 C60 superconductor, which is a FCC lattice of 3 times doped C60 molecules, which becomes superconducting at approximately 20 Kelvin. And these are very clear. This is an S-wave superconductor with very clear signatures in the optical spectrum. I don't need to explain to you about the plasma edge. I can read the book about a London superconductor and then look at the optical properties at equilibrium, and bada boom, you see the reflectivity becomes 1 below gap. The real part of the optical conductivity opens a gap. This red is above TC and blue is below TC. And then there's a delta function at 0 frequency that I'm not measuring, but I am signaling this because the inductive conductivity diverges like 1/omega toward low frequencies, which tells me that in sigma 1 I have a delta function. Okay? So this is what happens if I take the superconductor and I cool it at equilibrium below TC. The reason why this material becomes superconducting is that if I look at the lowest occupied molecular orbitals when I dope the buckyball 3 times, I have these 3 electrons, which without anything else would form a high spin state. But because of a Jahn-Teller instability, I have the formation of these singlet states. Here, actually, a linear combination of singlet states on each one of these 3 orbitals, and these are conducive to the formation of a superconductor. So this low spin configuration of the C63- allows you to have a superconducting state. And so what I know is that this particular distortion, what I would like to do, and this is how we started, although it's unclear whether this is what's really going on, is that we were thinking, okay, we do the right shaking, and then on average, we will displace the system along this Jahn-Teller coordinate, which will stabilize these pairs. And so, and we will make either a better superconductor or a polaronic insulator where nothing moves, where the pairs are really localized, or something between the two. So this is the experiment. You pump this particular phonon, which is a T mode, that then couples nonlinearly and presumably displaces along the second mode, which creates the pairs. And then we come with a second probe pulse to measure the appearance of the gap, provided that it appears. And so this is the result. This is what I showed you before. You take the 25 Kelvin superconductor. This is the red curve. Sorry, you take the metal at 25 Kelvin, you cool it, gap, reflectivity equals 1, 6 millieV gap, and divergence sigma 2. Now we go to 100 Kelvin, 5 times above TC, and we produce something that looks very similar to what you observe under cooling, except that the gap is now at least 2 times bigger than the equilibrium gap. And this happens all the way to, it really depends on the fluence, going back to Aditi's question. We used to think that this was fluence independence, but there's a lot more to this. And it turns out that this is what we published the last time. It seems to, this is equilibrium TC, and it seems to, you have a finite gap all the way to room temperature, and you can confidently say that the system looks like a superconductor up to anywhere between 150 and 200 Kelvin. So what is going on? I'm going to say 3 things, and then I'm going to show you, if I can, 5 minutes I have, great. I'm just gonna now say at least 3 things that might be happening that are good for superconductivity in this material. This is what we wanted to do at the beginning. You shake the T mode, by Q square Q you displace along the coordinate of the H mode, you form stronger pairs, you make a stronger gap, and if this is where in the weak coupling limit, you would get a better superconductor. That was the plan, okay? Except that if you talk to people that know what they're talking about, they say that this 20 Kelvin is the best you're going to get. If you make these pairs stronger, you will not make a stronger superconductor because you're in the strong coupling limit. For various reasons, you'll drive it into the polaronic state. So it looks like our initial hunch, which is always good to do experiments, it doesn't really bear on reality. There's at least 2 theories I'm very fond of. One is this work that has been put forward by the Columbia group, so Dante is going to give a talk later, and basically the idea is that if you have a chain of polaronic sites and you climb the vibrational ladder of a polaron, the correlation physics in the nth vibrational excited state of the polaron in presence of various nonlinear interactions can be very different, and in fact self-squeezing of the molecular modes given by the fact by double occupancy can give rise to a doubly occupied state that has lower energy than the singly occupied state. So this would be equivalent to a negative U state. Did I summarize it correctly, Dante? Good. The other thing that is my real absolute favorite is the one that is being put forward by the Harvard group, where they're discussing, and whether this is exactly right or is just morally right, I don't know. But what they're suggesting is that by modulating the Hamiltonian with quartic type of nonlinear interactions in the sense of nonlinear phononics, one might be parametrically amplifying the superconducting wave function. And hence, perhaps, maybe this is really what we're looking for, a situation which is very general, in which one has already fluctuations that are those of a superconductor, except that the system is not a superconducting state, and by driving I can amplify this broken symmetry state. And so the reason why I like this a lot is that this could in principle be applied to all sorts of broken symmetry states. And now I'm gonna sort of tell you a couple of things. This is new data that we put on the archive, and right. Okay, first, this is new data by my student Alice Cantalupi. First, the gap, this is now we've redone the experiments with much broader probing, because in the older experiments, we could really kind of see up to here with the gap, and the rest we had to imagine. So now we have a much broader probing, and it turns out that the gap is actually a bit larger than we thought it was, and that it really depends on fluence. So the harder you pump at some level, you get a little bit of a bigger gap. The gap looks actually nicer when you pump. This is the data I showed you before, and I said, oh, look at this. This is really 1/omega. This is the new data when you pump stronger. You can see, a much clearer gap feature and a much nicer 1/omega response in some way. So the other thing, which is the last thing that I want to show you, is that, there's in principle the presence of a gap and a divergent sigma 2 is compatible with a polaronic state with infinite conductivity, which has got a gap and has very high conductivity, but that is not a superconductor, okay? So in principle, until you measure the Meissner effect, you cannot tell the difference in the optical spectrum between a high mobility metal, although the mobility would have to be incredibly high, and a superconductor. One way that we thought that we could transiently try to discriminate between the two would be to look at the response. So this is the equilibrium gap in C60 when you squash it under pressure. This is pressure, and this is lattice constant getting smaller. If a superconductor was a metal, when you squash it, the effective mass would get smaller, the density of states would go down, and the conductivity would get better. But a superconductor in the weak coupling limit under pressure becomes worse. So what we're going to do are 2 slides for an experiment in which you redo the experiment under pressure to see whether the light-induced state gets better or worse under pressure. Right, okay, so this is just a bird-eye view of the data. Already at this was the light-induced state that I showed you before. Focus on this 1/omega response, which is the good one. Then you apply pressure, 150 megapascal, and then by the time you get to 300 megapascal, you already see that your sigma 2 has started peaking here, okay? And that the gap is progressively closing, and the state is becoming worse with pressure, as if it was a superconductor, okay? And you can also see this if you plot sigma 0, which is the extrapolation to low frequencies of your conductivity. You see that, and you apply pressure, you see that the superconductor gets worse and worse. The light-induced superconductor gets worse and worse with pressure, up to a certain pressure where it again gets better and better when it becomes metallic. Okay, so, and this is what happens at equilibrium, where you have a metal that always gets better, above TC, where you have a metal that always gets better with pressure. So this pressure data, which is really, you know, the life of 3 people, sort of that have almost died in the lab, shows that at least these observations are broadly consistent with, let's say, a complex many-body state in which making the mobility of the electrons higher reduces the properties of the system. And this is now we're starting to generate some sort of above TC phase diagram of a function of lattice constant. This part is the one we haven't looked at. This is cesium, this is rubidium. But this is this list, which means light-induced superconductivity, which decreases with pressure, just like the equilibrium does. And this is some sort of high mobility metal, for lack of a better word. Right, last. So very important people. So I would say for the cuprate work, so Van Zheng Hu was a postdoc with me for a long time. He's now going to join the BU faculty. Roman Mankovsky was a graduating student who's done all the X-ray diffraction determination experiments. Daniele Nicoletti, who's done all the optics, together with Stefan Kaiser and other people. And Alice, where is Alice? Alice Cantalupi that did all the pressure experiments. Thank you for your attention. Sorry for talking too much. This is sort of